All right. And for the sake of time, I might go on to Christian's talk, but Frank asked a good question in the discussion. We can take that offline in discussion.
All right, can you see my screen?
Yes, we can.
Great, thank you. So this work is part of Muri on cyber deception, and I have a number of collaborators there. One is Milind Tambe, who was once upon a time a sole person and since gained fame for games as a game theorist, in particular for the application of Stackelberg games to security problems. My colleague Cody Gonzalez helped collect the experimental data. And the bulk of the modeling work here is done by my postdoc, Drew Cranford, who has really done a fantastic job on this. So yesterday, we saw a number of questions and themes emerge. Some of those were, how predictive are cognitive architecture? Can they account for individual performance, not just average or normative performance? Can they be used to guide human-machine interaction? And can we also understand and explain them better, especially to non-practitioners of cognitive modeling? So we'll look at that on this particular task. And again, the goal of the Muri was can you see my mouse, by the way?
Yes, we can.
Okay, great. So the task was essentially a multi-arm bandit task where the cover story was an insider cyber attack. And there's the insider there in the middle. And he has a number of computer targets that he can decide to raid. Each of these targets is defined by a number of payoffs. So that's the yellow stars here, that's an attractive, but also the penalty if he gets captured. And he's also told, maybe from surveillance, and that's a key assumption of Stackelberg games, the probability of time that that particular computer is monitored. And it turns out there's 6 computers, there's only 2 analysts who can monitor them. So 1/3 of the time, a given computer will be monitored. That means that 2/3 of the time it will not be monitored and the attacker can attack with impunity. So the idea of using deception or persuasion in this context is to give a signal, a warning signal. And the interesting aspect is that that signal is sometimes true. It tells the attacker that, well, this computer is getting monitored. Do you want to access it? But sometimes that computer is, the warning is given when the computer is not monitored. So that's the deceptive part. And ideally, what the Stackelberg scheme tries to achieve is to maximize the effectiveness of the warning to convince the attackers to not attack as often as possible. And of course, you can see some of the time when no warning is given, that's pretty much a dead giveaway that the attacker can attack with impunity. So you have to be careful there exactly how much of the time you give the signal. And the default Stackelberg approach essentially gives it 2/3 of the time. It essentially drives the expected value of attacking, giving a warning to 0. And according to game theorists, then people will decide they don't want to attack. All right, so obviously we're going to model this with a cognitive architecture, and the ACTAR diagram that you see there is sort of color-coded as per the common model of cognition that John mentioned in his introduction yesterday. So obviously I'm not going to explain ACTAR, but the interesting aspect is, well, you have the cognitive architecture, you have a task, and as John just mentioned, well, there is a gap there between the architecture and the task, and that's where the things like models and instructions come into play. So to try and bridge that gap, we've adopted in many of decision-making paradigms an approach called instance-based learning. The idea that we don't make decisions based on any predefined strategies, clever or otherwise. We make decisions based on experience. Experience is something that the cognitive architecture naturally caches in memory. and then makes available according to sort of the regularities of the mechanisms that are defined here by those equations that most people are familiar with. In particular, this is the activation equation, including the base level term, the partial matching term, the stochastic term. Those define a probability of retrieving an outcome, one of those chunks, but often we use a mechanism called blending, which retrieves not a single experience, which is of course bound to be very noisy, but a consensus of past experiences which are similar as per partial matching to the current experience, and essentially extract an expected outcome out of that, that then is used for decision making. So you can view that this process here in the context of this particular problem. You can see the representation of the event, which is in this case the reward, penalty, and monitoring probability of that particular target, the potential decision to be taken, and then you extract out of memory, out of a set of instances, a consensus sort of outcome, and you use that consensus outcome to make a decision. So once you adopt that instance-based learning framework, the general logic of the model is very straightforward. You have a set of targets, you encode them each, and you generate an expected outcome according to that process that we just saw for attacking that particular target. You pick the one with the highest expected value. You could pick it stochastically, we could pick it deterministically, but of course there is stochastic component in the retrieval itself, so that seems to be sufficient for accounting for stochasticity. Then you get that signal that tells you sometimes whether the target is monitored or not. Then you have a second decision to make, whether you want to pursue with your attack or whether you're deterred and you essentially run away and you sort of like no harm, no foul, you gain 0. So for this, you again go through the same instance-based learning process, but this time representing the presence or absence of the signal. And from that, you generate another expected value. And if that expected value is greater than 0, which is the outcome of just running away, then you attack, otherwise you don't attack. It's a very straightforward model. There's very few degrees of freedom. And when you apply it to the task, it generates quite good results. So what you can see here, so the task is given for 100 trials of 4 blocks of 25 trials each. Each block uses the same set of targets with their particular payoff values and penalties and probability of monitoring, but each other round is a different set of targets. So there is some transfer across rounds, obviously. And you can see that the model does a quite excellent job at matching even the trial-to-trial variation. It turns out that the coverage and the signaling schemes are static. So there's really trials on which some of the targets are very tempting and a lot of subjects get caught, and then they're reflected in the next trial. So you can see the trial-to-trial variation is very good, as well as the individual population. So you can see here, that's the probability, bins of probability of attack from 0 to 100% of the time. And the popularity as a function of the percentage of the participants. And you can see that attacking almost all the time is actually sort of the strategy of about 50% of the population. But then the rest is very distributed all the way to attacking very seldom. And you can see that the model does a very good job at capturing that just through the stochasticity of making decisions in an instance-based learning way. Each retrieval is stochastic, each decision is stochastic, it creates a different outcome, and then that's used in the next cycle to make decisions. And you can see that the different model runs really follow very different paths that very much correspond to the distribution for subjects. And this, by the way, is for the trials where only those trials where the signal is present, not including the trials where the signal is absent. So that's a really good model of the task, but we have to be honest. Our first attempt at it, we didn't quite have the experimental data yet, so we actually published our model predictions. And our model predictions were these at the bottom as far as the distribution you just saw. And you can see that the model sort of captures a very good range, and those were predictions without seeing one bit of the data. but not that group there, that half of the subjects that attack almost all the time. So we really thought, okay, do we want to stick with a single model that captures the entire population or have a submodel? And we decided, well, let's try and see if we can do things to the model to get a slightly broader range. So the kind of things that you can do, that we did actually, is to take the initialization and the practice a bit more seriously. We had initialized the model with some chunks that we thought were reasonable, but we said, hey, let's give the model exactly the same practice round that the subject had 5 trials to warm themselves up. Let's take the information context effect seriously, which is, when you see the warning, you don't see anymore the characteristics of the target that you selected, payoff probability. Let's not represent those. Let's make a decision strictly based on the warning and not the rest of the context. And most important, don't clean things up. Listen to the architecture. The model generates predictions at every turn. And we figured, oh, we don't want to overwhelm memory with predictions. Let's erase them. So only the actual outcomes are in memory. I said, no, the outcomes are generated, the expected outcomes are generated. Let's let them compete together with the actual outcome on memory. And that gives rise to effectively a confirmation bias, where the subjects that are lucky early keeps believing that and keeps reinforcing that. And even if sometimes they get caught, that creates a momentum such that you actually get that about half of the subject as well that attack all the time. And that applies not just for this particular condition, which is the standard sort of deceptive warning according to the Stackelberg equilibrium, but also to a different condition, which you get the same warning, but you're also told the probability of time that that warning is accurate. And it turns out that doesn't change behavior all that much because it's very difficult to figure out what to do with that information. It also, of course, covers the situation where the subjects are given no warning. And it turns out that they pretty much, as the model does, attack all the time. Because the expected value, since the system can only cover 1/3 of the targets, the expected value for all the targets is positive. So attacking all the time is actually a valid strategy. So what we did, as it turns out, that the optimal Stackelberg scheme is actually not quite that effective at convincing human subjects, as opposed to ideal subjects to attack, is our collaborators, Milind and his group, came up with different game theory approaches to generate that signal. And what we can do once we had the model was to run the model with that new signal and make a priori prediction of whether that signal would be effective or not. And it was quite amusing because we tended to say, no, it's not going to work. And Milind didn't believe us. So we'd run the subjects. And sure enough, the model turned out to be, as you can see, the model turned out to be quite accurate at the various aspects of the data. So using models as synthetic subjects turned out to be a very practical and potentially very effective thing, considering the difficulties of running subjects, especially these days. But it's one thing to generate the whole distribution of subjects. But can we actually align specific model runs with specific individual subjects, a little bit in the same way that intelligent tutoring systems used to do? And it turns out that we can very much do that. And it's through a combination of model tracing, which at every step forces the model to make its own decision, but that forces it to follow the same decision as the subject, so that the instance base in memory keeps being aligned with the subjects and therefore the same basis for making those instance-based decisions. But also knowledge tracing, because the experience is not quite enough. If you have a misalignment early, you do need to infer what the basis of the subjects to make the decision might have been, that different decision, and align that accordingly, independently of making it sort of the model tracing of making its own, making the same decision. So when you do that, it turns out that the correlation between the human probability of attack and the model probability of attack becomes very, very good, 0.95. So that means that we have a possibility of using individual models to try and act on them. And in particular, can we develop a scheme, a cognitive signaling scheme, as opposed to a game theory signaling scheme that optimizes the signal to convince the attacker not to attack, that is optimized to that individual human subject, considering the great differences between subjects. So, and then the cognitive model seems to be a very good tool to do that, because it's a computational model that can be run forward and predict the effect of various courses of action. So that's what we did. There are a couple of different ways of doing that. One is to simply run the model in Monte Carlo mode. What we did instead, we used essentially a closed form version of the model to compute the trade-offs between the short-term cost and the long-term gains of the intervention. So the basic problem here is that humans tend to lose trust in the signal when they attack and they realize that the signal was defective. So you can try and restore that trust by giving blocks of truthful signals. But the problem with that is that then you're only signaling 1/3 of the time, and 2/3 of the time you're essentially giving the attackers a free pass. So there is a cost to that. And essentially what this closed form version of the model gives us is a principled basis for making those decisions of, for the next block of 10 trials, are we going to give a truthful signal to rebuild trust, or a deceptive signal to try and convince the attacker maximally not to attack? So as always, we applied that model. We applied essentially the cognitive signaling using the model against itself, and we generated predictions. So you can see here that the black line is the sort of the baseline there with the standard game theory signal. And the yellow line was our prediction using that cognitive model-based signaling. And the blue line is the human data that we got. And you can see there that the scheme was not as effective as we thought it would be. And you can see also that the subject, so this is the probability of given the truthful blocks over time, that the subject require many more truthful blocks to compare to the model to restore trust. And it turns out that the main discrepancy when you look at the population was that very large proportion of subjects, again, 40–45%, who keeps attacking all the time. So that's quite strange. So we decided to look a little bit closer at the questionnaire that we gave, the post-task questionnaire we gave subjects. And it turns out that a very large proportion, a significant proportion of subjects, reported completely ignoring the signal. And in particular, that was the case for those subjects that attacked at least 95% of the time. So we thought, okay, we made the decision early, as I mentioned, to try and account for the entire population of subjects through a single model, and we largely succeeded. But it turns out in this case, the adaptive signal seems to amplify group differences, and in particular in that key aspect of whether to pay attention to the signal and try to figure out when it's truthful or deceptive, or just ignore it altogether. So when we split the model into two versions, one is the original model, and the other is a version of the model where we just remove the representation of the signal from the instances, it turns out that the two versions of the model very nicely align on those two groups of subjects, the group that attacks almost all the time and the group, much more varied group that doesn't. You can see that in the probability of attack, which is now, the model is now a very good match to that that subset of subjects that seem to be adaptive enough and pay attention to the signal, and the model that ignores the signal is a very good match again to that group that just attacks all the time. And you can see that reflected in the distribution. You can see that reflected in the group's probability of getting a truthful blocks in the course of the experiment, as well as essentially their utility of how often they succeed or fail in attacking. So the last question that I mentioned was, can we explain models better? And on the one hand, this model is very simple. It's a cognitive architecture, an instance-based learning approach. The representation of the instances is quite straightforward. The logic of the model is quite straightforward. But when you see that kind of variation of experience and you wonder, wow, why does this run of the model attack all the time? Or why did it decide not to attack in this particular trial? Well, the reason is really in that soup of instances and their subsymbolic relation in terms of activation, recency, frequency, similarity of their values. And it's quite hard to impossible for a modeler to sort through those dozens or hundreds of instances and try to make sense of all the factors at play. So that problem of explaining models turned out to be very similar to a problem that two others of my postdocs, Sterling Stommers and Konstantinos Mistopoulos, had been working on in the context of the Explainable AI project. There we developed methods for essentially the opposite of what Greg and Laura were talking yesterday. Rather than using a cognitive model to train an AI model, we trained the cognitive model by observing, essentially building a mental model of the AI model. And then we developed a methodology called cognitive salience to essentially explain the salience of the various cognitive features represented, and that's an instance-based learning model as well, and how those features influence the decisions. So essentially the way it works is a little bit like backpropagation. You present an instance to an IBL model, it computes the activation and matching score of all the instances, their recall probabilities, computes the blending equation, then makes a decision. And essentially what salience is the backwards derivation through this chain of equations of the outcome, that consensus value to each of the features. And it's quite computable. It's basically the same complexity as the forward computations itself. So we thought we have this methodology that can apply to any IBL models. Let's apply it to this one. And it turned out to work quite nicely off the box. So that's the salience of the three features in the selection, which is the payoff or reward, the penalty, and the monitoring probability here in blue. And you can see, first of all, that the saliences are very much closely related. And that results from the fact that the game theory model has optimized the monitoring probability to reflect the various payoff and penalties of all the targets to even everything else. So that's not too surprising. You can see that the salience decreases over time to stabilize, and that reflects to the fact that when you're early and you have very few experiences, your decisions are likely to be noisier, i.e. have greater salience to particular individual decisions. And then you have interesting deviations. So this here, this undersalience of the reward is effectively a version of risk aversion emergent from stochastic decision-making that we saw in other models. And here, the bump in the salience of penalty reflects something that we'd observed before, the fact that round 3 seems to feature an inordinate amount of experiences where the attacks are unsuccessful and result to heavy losses. And we can see here that the saliences pick on that. But that's the average saliences. And as we can see, there are very significant individual differences between subjects. So let's look at the combination of saliences of the three factors for each subject. And here they're plotted, each subject is plotted as a particular point in that three-dimensional, that triangle graph that essentially reflects the axes of reward, maximum probability, monitoring probability, and salient, and penalty. And we color code each subject according to the dominant salience for that particular subject. And then we go and we look at their selections, and this is the reward penalty space. So each of these dots correspond to a particular target. So there were 6 targets, 24 total, 6 in each block and 4 blocks. And you can see that the size of those circles reflect the probability that the subjects of that group selected that target. And they're color-coded by the group. So the blue circles, and they're superposed on each other, so you can guess from the colors sort of which is larger than which. And you can see the monitoring probability group largely selects targets with low reward and low penalty, which according to the game theory optimization will also have low monitoring probability. You can see that the subjects that are primarily focused on reward select high reward target. And those that are primarily focused on penalties select high penalty targets. So you can see that the Salience provided some insights in the underlying patterns of the individual subjects. You can do
Christian,
this.
4 minutes.
Yep, no, I'm wrapping up here. So you can do the very same analysis with the attack bias. And again, you can see that the group of subjects that attack all the time have a lower salience of the signal that reflects the fact that they have an overestimate of the success. So wrapping up here, so how predictive are cognitive architectures? Surprisingly, at least, I'm still being surprised at how some of these models can account for both the average and the individual performance, at least on constrained decision-making tasks. Can they guide human-machine interaction? It seems that we can use models to tailor human-machine interaction and to optimize performance, again, on constrained tasks. In the wild, this is still obviously an open matter. And can we use techniques from explainable AI to provide understanding and explanations for the model's behavior? And I think that that is very much the case as well. And I'm wrapping up here with some references to this work. Thank you.
All right, thank you, Christian. We have a couple questions. Stephen asks, when talking about instance-based learning, you described an event representation or context. Does this have any relation to human mental models or for events?
That's right. Definitely, for example, in the explainable AI, that is our base assumption that that set of instances of observing an AI doing various kind of behaviors given various situation features is very much the base of the mental model. That doesn't suggest that there is nothing else. And in particular, the kind of causal relations that John talked about could also be part of the mental model. Whereas here, those are represented purely implicitly in the instance base.
All right, and Antonio asks, does instance-based learning use the same strategy of exemplars theory of learning and categorization, or does instance-based learning strategy add something more to exemplars-based models?
So you can think of categorization as a limited version of general instance-based learning decision-making, where the decision is strictly to assign the most likely category to the outcome. So you can very much have an IBL model, and indeed we had some in the past that worked exactly that way. The slight layer of complexity that's added here is the decision-making layer, which is fairly straightforward in this case, which could be more complex in general.
All right, thank you. Mm-hmm. Our next speaker is Matt Versaghi. We are at the time for starting our next talk, so we'll switch over screens.
All right, let me know when I can go ahead and steal the ball.
You can start whenever you like. You're ready.
All right, I am